We will design a column under axial compression with biaxial bending. As according to code, the design of column must take in account at least minimum eccentricity E minimum. If actual eccentricity E mu by pu is less than E minimum with respect to both major and minor axis of the column section, then eccentricity E should be greater of the following. Practically all the columns on the sides will be biaxial because you have to take in consideration the minimum eccentricity. So this is your PU, so this will be the EX and this will be the EY. Okay, so this EX should be greater than or equal to E minimum at least. Okay. Similarly, EY, right? Okay, E minimum X is equal to L by 500 plus D by 30, where D is the lateral dimension with respect to the X axis. And this should not be less than 20 mm. E minimum Y is equal to L by 500 plus B by 30, where B is the lateral dimension with respect to the Y by axis, but should not be less than 20 mm. Okay. So L is the unsupported length. For rectangular and non-circular, for non-rectangular and non-circular cross-section shape, it is recommended E minimum should be taken as LE by 300 but not less than 20, where L is the effective length of the column in the plane considered. Okay. A three-dimensional plot of PUR, MUX1, MUY1 is generated for different axes of bending and for different location of neutral axis. So this is our column. When the neutral axis is when the bending axis is along x-axis, then you will get a interaction curve, okay, in xz plane, that is uniaxial. That is for uniaxial moment about the major axis. When your bending axis is along y, then you will get an interaction curve along yz plane, which will be about y axis, right? The PUR is the ultimate load carrying capacity of a column for a particular bending axis and the depth of the neutral axis. And corresponding to this PUR, you will get the ultimate load carrying capacity MUX1 on the interaction curve about the major axis, and MUY1, the ultimate load carrying capacity of the section about the minor axis. Okay. So this is the load contour. Okay. So when you project this in XY plane, this is your XY plane. Okay. So it will look something like this, right? Okay. Code procedure for the design of biaxially loaded column. Code has adopted a simplified method based on brushless formulation for rectangular sections. This formulation can also be used for other symmetrical sections. This non-dimensional formula is as shown below. Okay, so this is the formula. MUX is the design moment, that is about major axis. MUY is the design moment, that is about minor axis. Okay, MUX1 is the ultimate uniaxial moment carrying capacity for the interaction curve about the major axis. Okay, MUY1 is the ultimate moment carrying capacity of the section about the minor axis for the corresponding PUR. Okay, both this MUY1 and MUX1 will correspond to the ultimate load carrying capacity PUR for a particular bending axis and a depth of the neutral axis. Right? Okay. So alpha in is a constant which depends on the factor axial compression force PU. Okay, this is PU, which we are considering it as PUR. Okay, so we are considering it as PUR. Okay. When PU is small, that is when PU by PUZ ratio is less than 0.2, then the load contour is approximated as straight line. Okay. So this is straight line where alpha n is taken as 1. Okay. Alpha n is taken as 1. Okay. When PU are large, that is when the ratio of PU by PUZ is found to be greater than zero point 0.8, then alpha n is taken as 2. Okay. Good. So this is the curve for that where alpha n is equal to 2, which will be a quadrant of the circle. The in between values of the ratio PU by PUZ, okay, between this value, you can find by this formula. Okay. What is PUZ? PUZ is found by this formula. But PUZ is the maximum axial load carrying capacity of the column under pure compression. Now, we will do we will do the design of a section or as a biaxial column. Okay, so we'll take this section, and the depth of the column is 500, width of the column is 300. This is our major axis. This is our minor axis. Okay. About major axis, there are three layers of steel: one, two, and three. There are six number of 25 diameters longitudinal steel in this column. Okay, and about the minor axis. Okay, and there are two layers of steel. That is one and two. We can see about major axis. We will take column as uh, reinforcement equally distributed on all four. It is the spacing, the steel is not exactly equally distributed on all four sides, but still uh, the results obtained will be much closer to this actual results obtained for this column. Okay. When we take the minor axis, we can see that the steel is equally distributed on two sides. Okay. So when we will consider the minor axis, and we will take the column as steel equally distributed on two face, okay, on two sides. Okay. So first taking the major axis, so the first layer is at 60.5 mm from the compression phase, and the area of steel is 982 mm square in that layer. Second layer is at 250 mm, and the area of steel is 982 mm square. The third layer is at 439.5 mm, and the area of steel is 982 mm square. Right? Similarly, we have minor axis. We'll see this later when we do the analysis. Okay. Now, we will try to do the design of this column, design the column section and check whether it is safe to carry following loads. PU is equal to 1200 kilonewton factor load. Okay. MUX is equal to 75 kilonewton meter factor load. This is MUX. And MUY is equal to 50 kilonewton meter factor load. This is MUY. Okay. FI is 415 and FCK is 25. Okay. So the first step is we have to check whether these moments are larger than that due to the minimum eccentricity. Okay. If they are not, then we have to take the moments due to the minimum eccentricity. Okay. Now let us check. Check for minimum eccentricity. Okay. Unsupported length is 3 meters. So E minimum X is L by 500 plus D divided by 30. D is 500. We get 22.67, which is greater than 20 mm. So E minimum X is 22.67 mm. Okay. Now actual E is MUX by PU. MUX is 75 kilonewton meter. PU is 1200, which turns out to be 62.5 mm, which is greater than minimum eccentricity. So we will take this eccentricity in design. That is why we will take this format in design. Okay. Now about minor axis. E minimum Y is L by 500 plus B by 30, B is 300. Okay, that is 16, which is less than 20 mm. Okay, now considering the actual eccentricity, that is MUY by PU, MUY is 50, PU is 1200, that turns out to be 41.66, which is greater than 20. So we will take this at eccentricity, and so we will take this moment as the moment, right? Okay. Now, first we will find the AS, that area of the longitudinal field, that is 6 number of 25 mm diameter, which turns out to be 2946 mm square. AC is area of concrete, okay, that is equal to AG minus AS. This is area, gross area, 500 into 300 minus area of steel, that turns out to be 147054 mm square. Okay. Now we have to find PUZ. Okay. This is the formula for finding PUZ. AC is known to us. Okay. AS is known to us. So PUZ turns out to be uh, 2571.3 kilonewton. Now we are taking PU equal to PUR, and that is 1200 kilonewton. So PU by PUZ ratio turns out to be 0.46669. Okay. So it falls between these two. So you will use this formula for finding alpha n, and so alpha n turns out to be 1.4449. Okay. So now MUX is known to us. Okay, this is 75. MUY is known to us, this that is 50. Alpha n is known to us, that is 1.4449. Now we have to find MUX1 and MUY1, which are the uniaxial moment corresponding to PUR, okay, for a particular depth of neutral axis, right? So we will do the analysis of this section, okay? Okay, so this is the section we are taking. Okay, this is major axis. So about major axis, there are three layers of steel, 1, 2, and 3. First layer is at 60.5, area is 982. Second layer is at 250, area of steel is 982. Third layer is at 439.5, and the area of steel in that layer is 982. So first we will give the data for this axis. Okay, so let us start. Okay, WD, that is 500 mm per center. WB is 300 mm per center. FI is 415 per center. FCK is 25 per center. Number of steel layers about X is 3. First layer is at 60.5 mm per center. Area of steel in that layer is 982 per center. Second layer is at 250 per center. Area of steel again is 982 presenter. Third layer is at 439.5 mm presenter, and the area of steel is 982 mm square in that steel layer. Now we have to give the data for all the steel layers about y axis. Okay, so this is our y axis. So there are two layers of steel, layer 1, layer 2. First layer is at 60.5 mm. Okay, so and the area of steel is turns out to be 1473. Second layer is at a distance 39.5, and the steel area is 1473 again. So let us give the data. Okay. So number of steel layers is 2. The first layer is at 60.5 mm. Area of steel 1473. Second layer is at 239.5. Area of steel layer is 1473. Okay. Right. Now our PU is 1200 kilonewton, MUX is 75 kilonewton, MUY is 50 kilonewton. Now let us Okay, so if this table shows the complete analysis of the section about when new- when the bending x when the neutral axis is moved uh, along about the okay. So analysis about x-axis and analysis about y-axis. Okay, minor axis and sorry major axis. This is major axis about major axis and this is about minor axis, right? Okay, so MUX is known 75, MUY is known 50, alpha and we found 1.449. Okay, how do we get this MUX1? Okay, we know we have to find the corresponding MUX1 for our PUR. PUR is equal to 1200. So, okay, PUR 1200, it comes in between these two. So the moment, corresponding moment will be in between these two values, right? You have to interpolate and find that turns out to be 202.6. Okay. And now about MUY1, right? So again, taking PUR is equal to 1200. Okay. So it falls between these two values, and the corresponding MUY1 falls between these two values. By interpolation, you get it as 122.93. Okay, so this is how this whole formula ratio turns out to be 0.51, which is less than 1, so it is safe. Okay, so this is how you can do the analysis of a biaxial column. Say suppose you don't have such tables, okay, so then you can use the code, the diagrams, PM diagram given in the code. Okay. Okay. Now about major axis, we are considering the column to be reinforced, equally distributed on all four sides, right? So first taking the about major, D dash is 60.5, D is 500. That turns out to be 0.121. So we will take the graph for 0.15. Okay, 0.15 is 415. Okay, now PT. PT we know the total area of steel AS is 2946, right? So put the value of AS over here and find the PT that comes out to be 1.964. Okay. Now PU by FCKPD, PU by FCKPD, okay, that turns out to be 0.32, okay, 0.32, okay. Now, which graph do we have to take? Then all this graph given are for PT by FCK. So PT by FCK is 0.078. So we will take the fifth graph, the first, second, third, fourth, and fifth graph, that is PT by FCK equal to 0.08, right? So when we draw this line and cut the graph, we get this coefficient as 0.105. Okay, mu by FCKPD square is equal to 0.105. Okay, okay. When you find MUX1, then MUX1 is found to be 197. 197. Okay, right. The actual value which we found was 202. Okay, and from this graph we got 197. A little bit difference is there because we are considering our section as reinforcement distributed equally on four sides. So minor error is there, okay, because of this assumption. Okay. Now when we come to minor axis, right? In minor axis we know that the steel is equally distributed on two sides. So we will take this graph, okay? So D dash by B is 60.5 divided by 300, that is zero point 0.2. So we'll take graph for 0.2, Fi415, okay. And PU by FCKBD is 0.32, 0.32. We'll take the graph, that is PT by FCK is 0.08, and we get the coefficient 0.109. MU by FCKBD square is equal to 0.109, which turns out to be 122.62. Okay, 122.62. And from analysis we got 122.9. So uh, this is a very good match. Okay, so By using this graph, we get this coefficient as 0.19, and by actual analysis, we get it as sorry, 0.519, and this is zero point 0.51. Okay. So this is how you can use the codal graph to design the biaxial column, right? Okay. Now, say the same section is of a slender column, okay? And then what are slender columns? Okay. When the ratio of effective length LE by least dimension of the column is equal to or greater than 12, then an additional moment due to P delta effect, okay, this is P delta effect, okay, uh, is also taken in account. Following formulas are given in the code are used to find the additional moment for about the major and minor axis, right? Okay. Additional moments as per IS 456-2000. The effect of slenderness is taken in account by IS 456-2000 through additional moment method. The additional moment due to lateral deflection are calculated by following formula given in the code. This is additional moment about the major axis, and this is a formula. Okay, where LEEX is the effective length corresponding to the major axis of bending, and this is the additional moment we get for about the minor axis. Okay, where LEY is the effective length corresponding to the minor axis of the bending. K is the reduction factor multiplied to the additional moment. Okay. Now we can see that every column section will have a balance. Will have a point where the section will be balanced. Okay, and at that point you will get the balance load and the balance moment. Okay. Now when your design load PU is found to be greater than the balance load PB, then it is found that the whole column is under compression, right? It is obvious that when the column is under compression, then its moment carrying capacity always increases. That is why, in such cases, the code allows us to multiply this additional moment with a factor k, okay, which will reduce the moment, okay, because the column is under compression, the whole column is under compression when your design load is greater than balance load. Okay. So, what is balance load? How to find the balance load? Okay. PB is the balanced axial load corresponding to the condition of the maximum compressive strain equal to 0.0035 in concrete. Okay. So, say suppose we want to find the balance load for about the major axis. Okay. So, the outermost concrete face under ultimate compression, the strain to be considered is yield strain, that is 0.0035, and the strain in steel outermost uh, layer of tensile steel is to be considered as 0.002. So this is the outermost tensile steel layer. Over here, uh, over here, over here, the strain is considered to be 0.002. Okay. Now this distance is our effective depth. This is effective cover, which we have taken as 60.5. Okay. So effective depth is known to us, strain is known to us. You can easily find the balance axiom, right? This is balance axiom. Okay. So we will do that while doing the solving this problem. Okay. Okay. So factor K is found by this formula: PUZ minus PU and divided by PUZ minus PB. PB is the balance load, that is for about major axis it will be PBX, and about minor axis it will be PBY. So PUZ, as we know, is found by this formula. Okay. So let's proceed. Okay. There can be two types of column, that is braced slender column or unbraced slender column. Okay. When the end moments are in opposite direction, then the column will bend in a single curvature. Okay. When the moments are end moments are in the same direction, then the column will undergo a bend which will form double curvature. Okay. So this things remain the same in case of unbraced column. Right? Now, code has given some relaxation uh, that when the column is undergoes a single curvature bending, okay, then the bending moment diagram will be like this: M2, M1, okay, and the larger moment of these two is to be considered as M2, and the smaller moment out of these two is to be considered as M1. Okay. When it is a case of double curvature bending, then M2 is a larger moment and M1 will be the smaller moment, but M1 will take a negative sign. Okay. So, first let us find the additional moment required for the slenderness ratio, for the slenderness of the column. Okay. Find the total moment for which the slender column is to be designed. Okay. Given to us, Pu is 1200 kilonewton, Mu2 about major axis is 75. Okay. Mu2, this is named as Mu2 because this is larger of the two end moments. Mu1x is taken as 40 kilonewton meter. Okay, and about minor axis, okay, Mu2y, the larger moment is 50 kilonewton meter, and at one end, at the other end is 25 kilonewton meter, right? So we will find the total moment. Total moment is additional moment plus M max. M max is obtained by uh, this formula. Okay, we'll come to this. F5 we are taking as 415, FCK we are taking as 25. Effective length with respect to the major axis we are taking as 6 meters. Effective length with respect to the minor axis we are taking as 4 meters. And so this divided by D is found to be greater than 12, so the column is slender in this direction. And this divided by 300, that is width, okay, is again found to be greater than 12, so it is slender in that direction too. Okay. Now column size is 300 by 500. Is we have six number of 25 dia bars longitudinal steel. That area turns out to be 2946 square. Area of concrete is gross area minus this area of steel, that is 147054 square. Okay. Now, first step is to find the balance XU. And after finding the balance XU, we have to find the balance load, right? So we know that at the outermost compressed phase, the ultimate strain has to be taken as 0.0035, and at the outermost steel layer, the strain has to be taken as 0.002. And this is our effective density, and that is 439.5. So solving the triangles, okay, we get the balance Na about x is equal to 279.68 mm. Okay, so this is 279.68 mm. Similarly, about y by axis, we get 152.41 mm. Okay, so this is 152.41 mm. And the depth is 239.5. Okay. So once we have find the depth of balance neutral axis, we can find the corresponding balance load, say in x direction. Okay, sorry, over here PBX. This is balance load in x direction. How do we find it, right? So for the neutral axis, balance neutral axis 279.68, we directly have to sit in table. Okay, 279.6. This is the depth of neutral axis. Okay, the 279.6 comes between these two values. By interpolation, we get the balance corresponding balance load. Okay, that is PBX. Okay, so that is found to be that is found to be 841 kilonewton. Okay. Similarly, PBY. Okay, so balance depth of neutral axis is 152.41. So we will see this table. Okay, 152 comes between these two values. So you have to find the corresponding PBY by interpolation. It will come between these two values, and that is found to be okay 679.2. Okay. So once you know PPX, you know PPY, you can find K. PUZ is known to us. You can find PUZ by using uh, the formula which we know. Okay, this is the formula. Okay, you know AS, you know AG, you know FCK, you know FY. So PUZ turns out to be 2571.52. So PU we know is 1200. Okay, kilonewton, right? PB, for finding KBX, we have to take over here PBX. Okay, so when you put this value over here, we get KBX equal to 0.8, that's for 0.7825. Okay, when you put the value of PBY over here, then you get the value of KBY, that is 0.724. Okay, so these are the reduction factor to be applied to MAX, and reduction factor to be applied to the MAY moment. Okay, additional moment. These are the additional moment upon major axis and minor axis. Right? So this is the formula for finding MAX. PU is known 1200, D is 500, LEX is given to us 6 meters, and K we know PBX is also known. So total additional moment comes out to be 33.8 kilonewton meter. Similarly, MAY, right? PU is 1200, B is 300 mm, LEY is 4 meters, okay, and K is KBY, that's 0.724, okay, so this turns out to be 23.168. Now we have to find M total, okay, M total is equal to additional moment plus MA. Now code says, okay, we are taking this case that the column is under uh, double curvature pattern, right? So code says mx is equal to zero point 0.6 into m2. M2 is the larger moment plus 0.41. M1 is the smaller moment. First taking the about the major axis. So what major axis? M2 is 75 and M1 is 40. So this is what I have kept over here. It turns out to be 29. Now this value should be greater than 0.4 M2. Okay, zero point 0.4 M2 turns out to be 30 kilonewton meter. This is less than this, so we have to take M max X as 30 kilonewton meter. Now Mx total is equal to MAX. MAX we get as 33.8. Okay, 33.8 plus mx x. Okay, that is 30. 30. So total comes out to be 63.8. But again, the code says m total should be greater than m2. M2 is 75. Okay, in this direction, but this is less than 75, right? So we will take mx total as 75, right? Okay, so this is how we get the design moment about the major axis m. Now let us find for the total moment about the minor axis. Again same formula, zero point 0.6 into 50, m2 is 50, okay, point into this this is minus sign because m1 is has to be taken as minus, okay. 25, okay, so 25. So this turns out to be 20, which should be greater than zero point 0.4 m2. Zero point 0.4 m2 also turns out to be 20. MUY total is MAY, okay, so 23.2, okay, plus M max y, that is 20, right? That is 43.2. Now mu total should be greater than m2, but it is not greater than m2 because m2 is 50. So we'll take mu total as 50. So this is how we get the moment about the minor axis. But please remember, both this moment should not be less than pu by e minimum. We have found that our eccentricity is greater than e minimum. Definitely our moment is also greater than pu into e minimum. So this is how you find the moments about minor axis, major axis, and pu is known to us, that is 1200, and we have to design a biaxial column for that. We have already designed for the same value, and we got the ratio is 0.51, which is less than 1, so it was safe, right? Now, if it were a unbraced slender column, then mu total is equal to additional moment plus the larger moment. Simple, okay? In both the cases. So mx total is 33.8, ma is additional moment, plus the larger moment, that is 75. So it turns out to be 108.8 kilonewton meter. This is the moment, design moment, that you will take about the major axis. Now, MUY total turns out to be MAX is 23.2, okay, plus M2Y. M2Y is 50, okay, so 50. So the moment turns out to be 73.2 kilonewton meter. So this is the moment which has to be taken about the minor axis. So we will have to design our section whether it is safe for carrying. PU is equal to 1200, MX, MUX is 108.8, and MUY is equal to 73.2. Okay, check that. Okay, we'll give the value quickly, fast. Okay, okay. 500 is D, 300 is W, B, phi is 4.5, second is 25, layers of steel is 3, first layer is 3.5, area of steel is 982, second layer is at 250, area of steel is 982, third layer is at 439.5, area of steel is 982, layer of steels about Y2, first layer is at 60.5, sorry, 5, area of steel is 1473, second layer is at 239.5, and area of steel is 143. Okay, moment load is 1200. Now M you execute to take it as 108.8, which we got total moment including additional moment, and MUI is 73.2 again. So we want to see, check whether this section is safe. Okay, okay, so it turns out to be 0.87, okay, which is less than 1. So section is safe to carry the section is safe as and slender column 2. Okay, so this is how we can design a biaxial column, whether it is short or slender, right? Okay, now for finding PBX as balance load, code has given a table 60, right? Uh, we can also find the balance load using this table, right? Okay, let us find PBX using this table. Okay. D by capital D is 0.121, so we'll take it as 0.15. Okay, 0.15. For rectangular section, okay, K1, okay, we are finding the value of K1. K1 is 0.196, 0.196. Now K2, find the value of K2, right? K2. Over here, we have considered the column, a rectangular column, which the reinforcement equally distributed on four sides. Okay, so for 0.15 and Fe 4.15, K2 value is 0.203. K2 is 0.203. Okay, now this is PT. Okay, PT we found as 1.964. So putting all this value we get PBX is equal to 8 to 1. Okay. And actual value which we got from calculation was 841. Slight, a little bit difference is there because we are assuming that the reinforcement is equally distributed on four sides, but actually it is not that case, right? In case of PBY, right, you have to follow the same criteria, okay? D by D is equal to zero point 0.2, so zero point 0.2, K1 is 184, rectangle section. K2, again, I am taking this is 0.028. Actually, you can, for finding PBY, you can take this uh, criteria because about minor axis, okay, is equally distributed onto both sides. Okay, so you can take K2 equal to minus 0.022. I have checked it afterwards. Then PV turned out to be exactly the same which we get, which we got from the analysis. Okay, but here, as I have considered as this criteria, so a little bit difference has been found. Okay, but when I took this criteria that K2 is equal to minus uh, minus 0.022, and PVY turned out to be this value. Okay, it matched very closely. So this is how you can use this table for finding PVX. Okay. So I hope you must have found this video helpful. Thank you. Okay.